Hi, I'm Will Stevens, and today I'll be talking about our lab where we observed an object at constant velocity. So, the main purpose of our lab is to observe an object at constant velocity, like I just said, and then we're going to compare it with a computational model in order to observe how that constant velocity motion interacts with our fundamental laws of physics, primarily Newton's second law. And what I found was that the observed motion is not actually at a constant velocity, which is due to a net non-zero force, as I will discuss later. So let's go into Newton's second law, as I stated before. So as we know, force is equal to mass times acceleration, and then you can break that acceleration into the change in velocity. And in our case, we have constant velocity, so that change is zero. When you plug in that zero, our net force should be zero as well. So now let's actually look at the scenario. I rolled a wheel across this desk, which the wheel is the system, and pretty much everything else is the surroundings, including the desk, air, room, whatever. And roughly it appears that it is going at a constant velocity. So then I set up a computational model, which used the time period that you saw in this slide from when it starts to ends. That's 1.8 seconds. And then we used the velocity, which was the initial velocity that the tracker observed from that wheel. And then I used the velocity I set the position equal to velocity times time. And then this is the position and velocity graph of the computational model. As you'd expect, position is constantly increasing and our velocity is constant as well. And again, that 0.42 meters is taken as the initial from our tracker. And here is the displacement that you can see from the tracker as well. It has a relatively constant slope, as we would expect, but you do notice it starts to arc off, and we will talk about that shortly. So I have plotted our predicted and observed paths, and you can see that there's a big difference, and that difference increases as time goes on. And due to that, we have a 0.7 meter difference between our observed and predicted. And well, what does that mean? That means we have a non-zero net force, which was not what we had wanted. And so again, we can see in my velocity from the tracker, I used the initial, but you can see it decreases, meaning there was in fact a net force that was not zero. So let's solve for that net force. Using our initial and our final velocity from that same graph, we can solve for that net force using that formula I mentioned before, the mass times the change in velocity over time. And then you solve that and you get a non-zero net force. In our case, we have a negative, very small, 0.00292 in the negative x direction. And so what does this mean? It means that in our computational model, it had some assumptions. It assumed that there was some sort of force that was counteracting that frictional force, whether it was pushing or pulling, it had to balance it out. And we cannot, however, differentiate what those forces were. It could have been a combination of forces, it could have been one, we don't know. And some sources of error that I could have possibly mitigated was that wheel, you can kind of see that it didn't go in a perfectly straight line. From our perspective, it did, but it went kind of back up towards the back of the desk, which you can see in this y direction displacement graph. And that, of course, would change our velocity magnitudes. So what if we instead put it in reverse? So we go from right to left, meaning our motion is now in the negative x direction. Well, that won't actually change anything besides the direction. The magnitude is all still the same, so we would still have a non-zero net force, as we said before, but it'll be in the opposite direction. So some conclusions that I thought were important was that assuming a net force of zero is frequently incorrect. That is just a pipe dream. And then also, in this case, assuming that net force of 0 overestimated the displacement because of that possible friction. So, and then I also noted that frictional force, or whatever force it really was, that was accounting for that net non-zero force, goes in the opposite direction of motion. All right, and thank you so much for listening.